Let us analyze few more continuous beam using the Carney's method. So this is another problem. Now here this continuous beam is having 3 span. So span AB is of 8 meter, span BC is of 6 meter, and it is being loaded by a moment. Moment is at the center. This is 80 kilonewton meter. We haven't solved any problem where the moment has been applied to a span. Okay, so we are going to solve this. Okay. Next, there is a span of CD which is cantilever, and it is loaded by 30 kilonewton at its free end. Okay, so looking at this, what we first have to do is to find out the fixed end moments. So as we know, on span AB there is no load, there will be no fixed end moments. So we need to calculate the fixed end moment in case of MF BA, BC and MF CB, right? So the equation to calculate the MFAB and MFBA, the fixed end moment in case of movement, was given to you. Okay, I hope you remember the equations. So even if you don't remember the equations, I have written over here. Okay, so but the first thing that you need to understand here is that whenever there is a moment that is being applied, we have to see which is the direction of that moment. So the direction of movement is here clockwise. So the reactions that will be developed will be of clockwise in nature. Okay, both will be positive itself. Now if this movement was in anti-clockwise directions, the reactions would have been in the anti-clockwise direction. Now what you need to do is you try to make a physical understanding of how it may behave. So for that, what we'll do is we'll understand that this element being flexible in nature. Okay, so if it is flexible, at this point if I try to apply a moment, so it will create a elastic curve like this, right? So if you are applying a movement in the clockwise direction, so here it will bulge out. Okay, so once this movement reaches to this side, again it will bulge like this. Okay, so this will be the elastic curve, this will be the nature of elastic curve. Okay, so you try to understand, if I apply a movement like this, we have to apply a reaction like this. Okay, and here the reaction will be in this direction. So whenever there is a clockwise movement being applied, the reactions will be also clockwise itself or positive itself. Okay, if it is in anti-clockwise direction, both the reaction would have been negative. Okay, so this is what we need to understand, and then let us go with the equation that we have. So the equation that we have is mb into 2a minus b divided by L square. So here ma into 2b minus a divided by L square. So what is a? A is the distance between the near end from to the point of moment being applied. Okay, so this distance is a, and let us consider this as far end. So the distance from the movement to the far end is b. So whenever you see any structure or any member which is subjected to movement, first you need to look into the placement of that movement, where it is being placed from the left and the right side of the support. Okay, so this is your member now. So this is a member BC which is subjected to a moment of 80 kilonewton at the center. So it means what? A is equals to 3 meter and B is also equals to 3 meter. So let me substitute m value is 80, B value is 3, and 2 times of A is 6, and again B is 3. After simplification, I got to know that it is 20. Now similarly, I can solve for the other side, it is also equals to 20. So you can use these equations itself in case of the anti-clockwise movement, but what you need to do is you have to change the symbol and you have to write it down. Okay, I explained you why it is so. Okay, now once we calculate the fixed end moment for all the elements, now let us go to the cantilever portion. The cantilever portion is subjected to 30 kilonewton at the free support. So because of that, the reaction that will be developed. Okay, so we know that summation of moments at C should be equal to 0. It means what? mCB should be equal to mCD, right? So first let us calculate how much is mCD, the moment due to this concentrated load on this cantilever. Okay, so the reaction at the cantilever end, at this end, will be equals to 30 into 2, which is 60 kilonewton. Now let us see what is the direction of that movement. The direction will be of negative in nature. So if mCD is negative in nature, mCB, if mCD is in negative nature, mCD should be equal to positive in nature, right? So that's why this is 60 kilonewton load. Okay, and this becomes 60 kilonewton being applied here. So like this, I have adapted this continuous beam in this manner. Okay, I have just modified it. Okay, so after modification, what I need to do, if I have to remove this cantilever portion, I have to apply a positive moment of 60 kilonewton meter over here. Okay, we have solved the fixed end moment. The next step is to solve for rotation factors. Okay, so to calculate the rotation factor, we'll consider joint B, joint BA, BC is there. We'll calculate the K factor, stiffness factor. So we have solved how much is stiffness factor, I by 8, 3 by 4, I by 6. So summation of K is done. Then you will solve the rotation factor. So rotation factor are minus 0.25, minus 0.25. Okay, the next step is to draw this diagram, Kani's diagram. So in Kani's diagram, B joint is connected by two members, so that's why I have solved the Kani's diagram only for B joint. For A and C it is quite simple, as you know. Okay, now once it is done, what we do is that above the line we write down all the fixed end moments. Okay, so once you write the fixed end moment, what I have done is that I have written here the moment of MCD, which is minus 60 here. Okay, so now already there is a 20 kilonewton moment been written here as fixed end moment. So in order to make this equal and opposite, what I need to do is that I have to apply an extra 40 kilonewton load over here, right? So 40 plus 20 will become 60. So MCB is 60 and MCD will be equal to minus 60. They are equal and opposite, they will get cancelled out. Okay, now if I apply a moment of 40 kilonewton meter at CB, I need to carry over half of that to BC. Okay, so I have carried over here, which is 20. So 20 has been carried over from CB to BC. Okay, so this is how we write down the releasing of joint C. Here what I did, I released this joint C. So from now onwards we won't be solving anything over here, because we already have determined how much is the value of MCB has been already calculated. Okay, right. So now if this has been released, the next thing what we did was carryover. So once the carryover was completed, next what we do is that we will take the summation of fixed end moment at joint B. So when you are solving for fixed end moment, you have to consider both the carryover moment and also the fixed end moment. So 0 plus 20 plus 20 is 40. Now 40 is multiplied by the respective rotation factors, and the rotation moments are written over here. So as there is no need for another iteration, okay, because this is by only 2 span. If the span would have been more than 2 span, we would have continued for another few iterations. Now there is no need of iteration. What we do is that right now it is balanced. So minus 10 and minus 10 are written, with are the rotation movements at the near end. Next is to calculate how much is the rotation at the far end. To do that, what we do is to carry over. So from here to here it has been carried over, from here to here it has been carried over, from here to here there is no carryover, because this is already been released. At the released end we don't carry over. Okay, so the carryover is equals to 0. From this side to this side, again the carryover is equals to 0. Okay, now as we know, how do we calculate MIJ values? So if this is MAB will be equal to MFAB plus of 2 times of M double dash AB plus of M double dash BA, right? So we know MFAB is equals to 0, 2 times of M double dash AB is equal to 0, M double dash BA is equals to minus 10, so that is the value of MAB. Now similarly here also 0 plus 2 times of 10 plus 0 will be equal to 20. Similarly here 20 plus 20 minus of 2 times of 10 will be equal to 20. So 40 plus 20 is equals to 60, and that side 60. So this completes the end moments for this Q1 beam, right? So we'll go to the next problem. So let us solve this another problem. So again this is a continuous beam, so which is having a span of AB, BC, CD and DE, DE being the cantilever section, and for cantilever section we have a concentrated load at its free end. Okay, the question will be written in the description. You can read the question in the description also, but initially what I'll do is that I'll read the question from the question paper. Okay, so this is one of the question which was asked in a question paper, so I'm trying to solve this. the same question will be also written in the description. You can go back and refer the question there also, but right now I'm going to read the question. So this is the diagram which was given to you. So this continuous beam will be having a span of AB, BC, CD and DE, DE being the cantilever. Okay, now let us let me read the question and then we will try to evaluate what the question is being asked to you. Analyze the continuous beam as shown in the figure. The yielding of support permits a clockwise rotation of 20 by EI at A and downward settlements of 100 by EI and 200 by EI at B and C respectively. Okay, so let me read the question again, or else you can go to the description section and read the question. You can pause the video, go and read the question from the description, understand the question, then we can come back and solve this problem. Okay, so I'll read it again for your understanding. Analyze the continuous beam as shown in the figure. The yielding of supports permits a clockwise rotation of 20 by EI at A and downward settlements of 100 by EI and 200 by EI at B and C respectively. Okay, right. So what I will do is that I have written here yielding of supports. Yielding of supports may be of rotation or it may be of settlement. Okay, so rotation and settlements both are in the nature of yielding itself. Okay, so they are saying that support A is yielding with respect to rotation. So this is not sinking or this is not settling. So what basically happening at joint A is that it is undergoing a rotation. So that rotation is 20 by EI, he is saying. Okay, so let us note down this as 20 by EI at A. The type of yielding is rotation. Okay, next going to joint B. So joint B and joint C are settling down. Okay, so the settlement is 100 by EI at B, and at C the joint is settling by 20 by EI. So in all the previous video when we were solving for settlement, I used to give a value of settlement, okay, in terms of mm, and I used to give what is the value of E and I value. From that basis you used to calculate how much is your moment due to settlement, okay, moment due to translation. Okay, anyhow, now in this problem he has given you the value of 100 by EI. Now do not get confused with what this value is and how to solve it. Okay, we'll go with one by one. So just remember this and write down the yielding of support. At joint A we have rotation, at joint B and joint C we will have settlement. The values are given to you. At the rotation at A is 20 by EI, the settlement at B is 100 by EI, and settlement at C is 200 by EI. So EI is the value of Young's modulus and moment of inertia. So as we know, for member AB the moment of inertia I is 0.75 times of I, and for B it is I, and for CD it is I itself. Okay, now so first of all let us just calculate the fixed end moments for all the members. So for member AB, MFAB, MFBA will be calculated. Now member AB is subjected to a load of 6 kN UDL, 6 kN per meter UDL. Member BC is subjected to 3 kN per meter of UDL, and member CD is subjected to a concentrated load of 60 kN at the center. So respectively you can solve the fixed end moments. I guess there is no difficulty in solving the fixed end moments for MFAB, MFBA, MFBC, CB, CD and DC. So once you solve the fixed end moments, now let us try to resolve the moments that are created because of the rotation, the moments that are created because of the settlement. Okay, now let us focus on solving the moments that are created because of the rotation. I had solved a previous problem where I had considered the rotation of any of the joint. Okay, if you remember that, you can go back and see how I solved that. In a similar way I am going to solve here also. So what I'll do is, in the given problem they had told that joint A is supposed to rotate by 20 by EI. So the theta A value will be 20 by EI. Okay, now what will be the moment that will be created because of that theta A? So to solve that, we know that the equation is 4EI theta A divided by LAB. So if I apply a moment of 4EI theta A divided by LAB, the far end moment will be 2EI theta A divided by LAB. So let us first calculate how much is the moment that are created because of only rotation. Okay, so now I have written here m double dash AB. I told you that whenever I write m double dash, those moments are representing the moments due to rotation. So the moment due to rotation at A is m double dash AB is 4 EI theta A divided by LAB. So 4 EI. So what is the I value for AB member? It is 0.75 times of I. Now what is theta A? Theta A is equals to 20 by EI. Okay. So 20 by EI you need to substitute in here. So EI will get cancelled. If you resolve this, you will get to know that m double dash AB is 6 kilonewton meter. Okay. Now the near end rotation moment is 6 kilonewton meter. So how much will be the far end rotation moment? You can directly solve it by sending it half of that. Okay. So if I apply a moment of 6 kilonewton here, half of that will be supplied to that side. So that's why the m double dash BA, which is the far end rotation moment, is 3 kilonewton meter. Okay, or else you can solve by this equation also, 2 EI theta A divided by LAB, substitute the value of I, substitute the value of theta A, which is 20 by EI, and you can solve it and you will get the same value. Okay, so anyhow, as you know that if I apply at the near end a moment of 6 kilonewton, at the far end the moment that will be supplied will be equal to 3 kilonewton meter, which you know already. Okay, I guess there is no doubt in calculating the rotation moments. Now let us go and solve for settlement moments. Okay, so he has given you that the settlement is going to be downwards. So downward settlement is 100 by EI at B, and at C it is 200 by EI. Okay, now this is the original position of B and C. After settlement, this becomes your B dash, this becomes your C dash. Now first what I'll do is I'll first calculate for m dash BA. M dash is representing the moments due to translation or settlement. Okay, so m dash BA is here is minus 6 EI delta divided by LAB square, and the carryover to the far end will be also minus 6 EI delta divided by LAB square. So first let us calculate what are the moments that are created because of the settlement at joint B in member AB. Okay, so m dash BA, m dash AB, m dash BA will be equals to minus 6 EI delta B divided by LAB square. What is delta B here? Delta B is 100 by EI. Okay, so this translation will be 100 by EI. Now let us substitute what is the value of I and delta B in the equation, and we will solve it. It is equals to minus 4.5 kilonewton meter. So this value which is m dash AB and m dash BA are minus 4.5 kilonewton meter. So once you solve the moments due to translation for member AB, let us solve the moments due to translation for CB. I told you earlier also, you need to bifurcate the spans which with respect to the near end and far end. Okay, so what we do is that if the near end is at higher elevation, far end is at lower elevation, there you consider the moments to be negative. If the near end is at lower elevation, if the far end is at higher elevation, what we do is that we consider it to be positive in nature, right? So this is your near end which is at lower elevation, this is your far end which is at higher elevation. So what we do is that here we will calculate the moment. Now the far end is not fixed here. If it was fixed, this value of rotation would have been 6 EI delta divided by L square, but I have given you in the previous problem what is the moment of translation if the far end is pinned. If the far end is pinned, the moment that is created here will be equals to 3 EI delta divided by L square. Okay, now let us solve how much is m dash CD. Okay, now what will be m dash DC? As we know, this is pin joint, so at pin joint the value will be equal to 0. Okay, so the moment due to translation at in member CD will be solved over here. Now let us solve for m dash CD, because we already know m dash DC is equals to 0. So here it is equals to 3 EI delta C. I have to consider delta C. What is delta C? Delta C is the settlement at joint C. Okay, so 3 EI delta C divided by L square. Now we know how much is the I value for member CD. Member CD I value is I itself, and delta C is 200 by EI. So 200 by EI is substituted, and L is also substituted, which is 20 meter. Okay, 20 meter. After substituting that, I got to know how much is m dash CD, which is 1.5 kilonewton meter, and we already know m dash DC is 0. Okay, now I told you that when you are calculating for this mid span, okay, when there is a settlement of B and C, and when we are calculating the moments due to settlement at B and C in span BC, what we need to do is that we have to take the difference of this is your delta B, this is your delta C, right? So we need to calculate how much is this difference. So this difference will be equals to delta C minus delta B, right? So that's why when you are calculating the moment for member BC, okay, so here m dash BC is equals to m dash CB is equals to minus itself, so minus of 6 EI. So here the value of delta, so this value delta will be equals to delta C minus delta B, okay. So we know how much is the value of delta C, which is 200 by EI. We know how much is the value of delta B, which is 100 by EI. So I have substituted the same over here and I have solved how much is m dash BC and m dash CB, which is minus 6 kilonewton meter, okay. So now we know whether it is positive or negative. How do we see it is positive or negative? If the near end is at higher elevation, far end is at lower elevation, then we will see that the moments will be of negative nature, right? So the moment due to settlement in member AB, member BC will be of negative nature. In case of member CD, it will be of positive in nature, right? So now I hope this is very much clear. If you have any problem with solving the moment due to rotation, moment due to translation or settlement, you can ask me the question, okay. So by this we have solved the fixed end moments, we have solved the moments due to rotations, we have solved the moments due to fixed end due to settlement or translation. Then the next thing is to solve for rotation factors, right? So to solve for the rotation factor, what we need to do, we need to consider the joints which are connected by more than one member. So joint B and joint C are connected by more than one member. Joint B is connected by BA and BC. Joint C is connected by CB and CD. Let us solve for the stiffness values of member BA. Member BA is having a I value of 0.75 I. The length of the member is 10, so 0.75 I divided by 10. So in case of BC, it is I by 10. For CB also it is I by 10. But when you go for CD, the far end is being pinned, so that's why 3 by 4 I by 20. Length of this member CD is 20, right? So we'll take the summation of stiffness value of BA and BC. We'll write the joint stiffness of B. Similarly, the joint stiffness of C is calculated. So the stiffness of BA divided by stiffness of joint B multiplied by minus of half will give you the rotation factor for BA. So like this, I have calculated the rotation factor for BA, BC, CB and CD, right? I hope you remember how to calculate the rotation factor. So this is how we have solved the rotation factors, moments due to translation, moments due to rotation, moments due to fixed end moment, okay. So once you solve this, next step is to draw the Carney's diagram, okay. After that we can solve the end moments. So after solving all the fixed end moments, next is to derive our end moments. So to solve the end moments, what we do is that we draw this Carney's diagram. So in the Carney diagram, as we know, there are two joints which are connected by more than one member, member B and member C. So we have also calculated what is the rotation factor for member BA, BC, CB and CD, okay. And now I hope you remember this this diagram, where at this box, in this space, in this compartment, I am going to write the rotation factor for member BA. In this compartment, I am going to write the rotation factor for member BC. Similarly, for CB and CD, I have written the rotation factors. Now, you might not be able to see these values clearly, so I want you to refer the rotation factors that we solved earlier, and with respect to that, you can calculate the numbers, okay. So if you have any doubt with this, you can ask me the question later also, okay. Anyway, these are rotation moments which I have written here. Next, as I told you, above this line we are going to write all the fixed end moments. Below we will calculate the rotation moments. So before we come back to this, first what we will do is we will start on writing all the fixed end moments, okay. So I hope you remember the fixed end moments that we solved. So what you do is that we know MFAB, MFBA, MFBC, CB, CD and DC are to be written, okay. So let us write all the fixed end moments. Once we complete writing fixed end moments, next is we will write the moments due to rotation, okay. Now above the line of fixed end moment, whatever the rotation moments that we calculated, okay, I hope you remember that we have calculated the rotation moment for m double dash AB and m double dash BA. Those values are to be written next, Okay, so these are the rotation moments. Now in the question paper it is given that the rotation is taking place only at joint A, henceforth m double dash AB is there, m double dash BA is there, but for the other members there is no rotation movement, so that's why I kept m equal to 0, right? So there are no rotation movement for m double dash B, C, CB, CD and DC. Okay, so that's why the rotation moments written in this row. Okay, so once you write the rotation moment, in the next row we are going to write all the rotations because of the translation, right? So we know that because of the translation at joint B and joint C, we have solved the translation moments minus 4.5 as m dash AB, m dash BA. Similarly, m dash BC and CB has also been calculated. M dash CD is there, m dash DC is already equal to 0. So in the next row above the rotation moments, we are going to write the translation moments. Okay, once you write the fixed end moments in the first row, so I have represented by the black symbol. As you can see, I have written it by black numbers. Okay, so these are representing my fixed end moments in the first row. The row above that is representing the moments due to rotation. The row above that is representing the moments due to translations. So once you write all of them, the next step is what we do is that we'll go to joint which is pin joint. Now it has a cantilever portion. Now the cantilever portion was subjected to a concentrated load of 6 kilonewton and the length of the cantilever was 2. So let us solve how much will be the moment reaction at the cantilever end. So if I solve the moment reaction here, it will be minus 12. So I have to release this joint. To release this joint, what I have to do, if this is my MDE value, so MDE value is minus 12, I have to make MDC also equal to 12, but the symbol should be opposite to it. So if this is 12, I have to make, if it is minus 12, I have to make the moment MDC equal to 12, positive 12, so that I can release this joint completely. Okay, so now what I'll do is I'll apply minus 28 over here. So if I apply minus 28, 40 minus 28 will give me positive 12. So it means what? This moment is plus 12 and this side moment is minus 12. Now this joint can be released. Okay, now this is what I have done. I have applied minus 28 over here and 40 minus 28 will give you 12. 12 minus 12, m summation of moment at D is equals to 0. Okay, now when you applied minus 28 to m DC, you need to carry over that to the other side, which is minus 14. Okay, now I carried over it to CD also. Now once this step is completed, what I do next is to find out the summation of fixed end moment at joint B and joint C. So see here, what I did in this step is that I summed up all these values. Okay, for any given joint, if this is joint B, at joint B I have summed up all the fixed end moments. 50 plus 3 minus 4.5 minus 6 plus 0 minus 25 will give me the summation of fixed end moment at joint B. Okay, now which I have calculated the value. So summation of fixed end moment at B is 17.5. Now the next is to calculate how much is the summation of moment at joint C. At joint C, what we do is that we'll take the sum of all the fixed end moments. So minus 6 plus 0 plus 25 minus of 14 plus of 1.5 minus of 40 will give me the summation of fixed end moment at joint C, which is equals to minus 33.5. So after solving the summation of fixed end moment at B and summation of fixed end moment at C, next step is to keep on calculating our rotation moments. Okay, now let us continue with the first iteration of our rotation moments. So in first case, what I do is that at joint A, as I already know, it is fixed joint, so let me consider here the value of rotation moment equal to 0. So after that, this end, we do not know how much is the moment, but initially let us consider it to be 0 and let me solve the rotation moments for m double dash BA and m double dash BC. Okay, so when I am calculating for BA, what I do is that the summation of fixed end moment plus of far end rotation moments multiplied by the rotation factor, I will write the value here. Similarly, for solving for m double dash BC, summation of fixed end moments plus of summation of far end rotation moments multiplied by the rotation factor I'll write here. Okay, now 17.5 plus of 0 multiplied by 0.214 minus of 0.214 will give me the value of rotation factor for BA. Similarly, the rotation moment for BC will be equals to 17.5 plus of 0 multiplied by minus of 0.286 will give me the value of rotation moment for MBC. Okay, now this completes our first iteration. So next what we do is that we go to joint C. So in joint C what we do is that we take the summation of fixed end moments. Okay, so this plus of this value, which is minus of 5.005, okay, multiplied by the rotation factor. I'll write how much is the rotation moment at joint C. Okay, now the CB value, the rotation moment CB is 14.015. okay, similarly minus 33.5 minus of 5.005, here already it is 0, you have to neglect it, multiplied by the rotation factor which is minus 0.136, I have written 5.236. okay, now this completes our first iteration. So we'll go to the next iteration. In next iteration what we do is that again we'll go to joint B. Now in the first step we consider the rotation factor, the far end rotation moment as 0 at this point, right? But now after solving the first iteration we came to know the rotation moment is 14.015. Now that's why we'll continue this process in which 17.5 plus of 14.015 plus of 0 multiplied by the respective rotation factors will write down the rotation moments at joint B. Now coming back to joint C, what we'll do again, the summation of fixed end moments. Now as you can see, the far end rotation moment for joint C also has been changed. Earlier it was 5, now it is 9, right? So minus 33.5 minus of 9.0113 multiplied by the respective rotation factors, I'll write down the rotation moments. Now you will continue such steps till you reach the more precise decimal values. Okay, if you go and see the decimal values here, the earlier step also from the earlier iteration it was minus 7.088. In this step also it is minus 7.092. Now you can see that all the numbers are not varying that to a great extent, so the variation is just in the decimals, so we can freeze at this point. Now let me call all these values. So all the values which are written, all the numbers which are written in blue pen are your rotation moments at the near end. Now let us calculate the rotation moment at far ends by carrying over. So if it is minus 7.092, we have to carry it over to AB, right? So here it will be minus 7.092, here it is 0, so if I carry over it will become same. So now the carryover has to be done from BC to CB, CB to BC. Now BC to CB and CB to BC has been done, but here we don't do. I guess you remember in case of moment distribution method also, we don't carry over in case of pin support, right? So we are not going to carry over here. So as we know here, we are not calculating any rotation moment, so the rotation moment from far end is also equal to 0. Now this completes your iteration process. So after you complete all the iterative steps, what you do next is to solve the end moments. So I have written here the end moments. So the end moment that I can calculate by taking the sum here is MAB, MBA, MBC, MCB, etc. Okay. Now let us go to MAB. So to solve MAB, what we need to do is that we need to solve for MFAB. Okay. So what will be MFAB here? So let me call this as MFIJ. So to solve for MAB, what we need to do, we need to take the sum of fixed end moment, rotation moments, and far end rotation moments and near end rotation moments, right? Right. So this is your fixed end moment. So you need to take the sum of this, and that will give me the fixed end moment at joint A, B. Okay. So minus 50 plus of 6 minus of 4.5 will give you the fixed end moment at AB. So I calculate how much is MFAB. So once you solve MFAB, the next step is to solve for 2 times of M double dash IJ. So what is 2 times of M double dash IJ? Here it is 0. So this is the value which we have calculated. So here it is 0. So 2 times of 0 is anyway 0. So 2 M double dash IJ is 0. The next is to solve for M double dash JI. M double dash JI is representing the far end rotation moments. So the far end rotation moment which I have carried over and I have written here, M double dash JI is minus 7.092, if I take the sum of all of this, I'll get to know how much is the end moment. So the end moment at AB is minus 55.6. So MAB is minus 50.6. Now we can similarly solve for MBA. So how do we solve for MBA? So to solve for MBA, what we need to do is that we need to take the sum of all this. I'll write that as my fixed end moment. Next, what I do, this is your near end rotation moments. So we had to multiply it by 2 and I had to write down how much is that. Now you know that the far end rotation moment is 0. I have written similarly 0. If I take the sum of this, I can calculate how much is MBA. Now similarly for MBC also, let us take the sum of all this. Minus 25 plus 0 minus of 6 will give me the fixed end moment at BC, so which I written minus 31. Now the near end rotation moment is minus 9.47. I have to multiply it by 2 and I have to write the value over here. Now similarly the far end rotation moment is 15.641. I have written here, and if I take the sum of this, I can be able to calculate how much is MBC. Similarly you can calculate for MCB and MCD. So once you solve for MCB and MCD, MDC, which you already have calculated, right? So you have completely released this joint. So after releasing itself, you came to know that MDC is equals to MDE, which is equals to 12, right? So we have solved it. Okay. Now this is how we have solved end moments in case of this continuous beam using the Kani's method. So if you find any difficulty in solving this, if you find any doubt while solving this, you can ask me the question. We will have an interaction class. In that also we could be able to discuss. Okay. Thank you.